Presence. The integration of OPTEX, Optimization Expert System, and GAMS, General Algebraic Modeling System. Case, high/power, enterprise-wide optimization system. Electricity and natural gas dispatch. Hypothalamus artificial intelligence, high. Digital transformation powered by real-time autonomous and intelligent algorithms. In the video, high power, enterprise-wide optimization system mathematical models. The interested party can review the entire conceptualization process of high power, enterprise-wide optimization system. All models that integrate high/power have been developed using the OPTEX GAMS interface. The integration of the models is carried out automatically by OPTEX, and the generated programs coordinate their communication through the database, using monolithic models, or in RAM memory using large-scale parallel optimization. All high/power models can run in deterministic, or stochastic, version with user-definable uncertainty dimensions. Models can be solved using large-scale technologies, such as variations of Bender's theory, or Lagrangian relaxation, using parallel optimization to simultaneously solve all the problems in which the monolithic model is atomized. Finally, it is possible to introduce new models into high power as required. At Hypothalamus Artificial Intelligence Incorporated, HAI, headed by its founder and chief scientific officer, Dr. Jesus Velasquez Bermudez, we are proud to accumulate more than 50 years of experience in computer programming, artificial intelligence, mathematical programming, and operations management. HAI is a spin-off of a Colombian company, which operates as a knowledge factory in advanced mathematical modeling. Our intellectual property is born from practice. We have a comprehensive view of mathematical modeling in Industry 4.0, focusing on artificial business management, autonomous AI that guarantees objective decisions, artificial brains, integrates organizational decisions based on neuroscience, enterprise-wide optimization systems, EWOS, customized AI that integrates multi-problem model systems, and high-complexity mathematical models, traditional models that are part of our artificial brains. HAI is interested in establishing business agreements with organizations committed to highly complex mathematical modeling, such as commercial partners or GAMS users. This presentation is geared towards understanding the benefits of linking our OPTEX optimization platform with GAMS optimization tools. Link OPTEX to IBM Planning Analytics. HAI-UL, HAI-SGO and HAI-GAS together and make high power that is set simulation models optimal dispatch of electricity and gas systems. HAI-UL, electricity supply chain optimization, models designed to support the decisions of the various actors involved in the electricity supply chain. HAI-SGO, smart grids optimization, models designed to support the decisions of the various agents involved in the smart grids business. HAI-GAS, natural gas supply chain optimization, models designed to support the decisions of the agents involved in the natural gas supply chain. OPTEX's multi-problem model capability implies that the union of mathematical programming problems generates a new model, or a variation of an existing model. In this case, two models are formulated: electricity dispatch and natural gas dispatch. These fundamentals give rise to modeling based on multiple optimization problems, which is the holistic foundation of an organization, called enterprise optimization. The diagram presents what happens when this model is solved optimally. The two problems exchange information, either occultly in a monolithic model, or explicitly in a partition model. These fundamentals give rise to modeling based on multiple optimization problems, which is the holistic foundation of an organization, called enterprise optimization. The diagram presents what happens when this model is solved optimally. The two problems exchange information, either occultly in a monolithic model, or explicitly in a partition model. Multi-problem modeling without problem limits is what facilitates the theory of multi-problem models, which in turn are the basis of artificial brains, as it allows us to join, divide or modify problems, when necessary and possible. In this way, the core of problems that define high power can be formed, which is electricity, gas and water. The artificial hypothalamus of high power dispatch is composed of same systems. In general, In an artificial hypothalamus, each model can be associated with a type of model. All models communicate via a database, in RAM, or on disk, making complex models as a Lego game. The expert optimization system is supported by the artificial hippocampus, which stores structures and processes for scientific decision-making that must be permanently consulted. It stores, like in humans, the experience and the knowledge acquired over time. In the case of model formulation, a modeler should not repeat work every time he modifies a model. The joining, or splitting, of the models is done by keeping the records in tables. That is, in practice, formulating a problem is selecting, by clicking, the equations that compose it, in the same way models are formulated, as if they were a Lego model, which are formed by a set of equations, the Lego pieces. After OPTEX first deployment, the expert system was extended to store the history of all executions of a model, so that this information is used to perform hot starts of the models, accelerating the solution time. Electricity supply chain optimization. Provide a summary of the material used in this presentation. There are many documents, which can be provided by about high power. In this way, they will be able to learn about the advantages, and the technical details, of our mathematical models. To learn more about OPTEX, those interested can watch the video, Not Programming, the Dream of Every Programmer. Physical modeling, hydro system. High water corresponds to a general model that includes all kinds of hydraulic components, reservoirs, hydroelectric power plants, pumping stations, pumping storage, rivers, overflow channels, connection points, demands, irrigation, aqueducts, environmental, industrial. Components can be freely linked to form any topology. Hydroelectric power plants are modeled independently of reservoirs, so plant-reservoir and reservoir-plant connectivity must be established. The regulation capacity of the reservoir is simulated in detail, so such a simulation consistently represents the dispatch of the power plants, considering their ability to regulate the multi-annual, annual, hourly water resource. For special reservoirs, it is possible to generate established operating rules based on agreements or laws that must be observed when using water resources. Electrical system. Electrical connectivity is carried out through a network of circuits, links, and bars, nodes, that integrates different types of installations, power plants, hydroelectric, thermoelectric, coal, wind, solar, biomass, places of demand, industrial, cities, regional interconnections and energy storage. For each type of electrical infrastructure, high power includes the exact equations for simulation. High power includes the simulation and several types of renewable energy sources and energy storages. Gas system. High gas describes the process of supply and demand of natural gas. From this point of view, its integration with the electricity system determines the economic balance electricity-gas. The entities of the natural gas system are: node, connect the gas system installations. Production fields. Consumption zones, discriminated by sector, example, refineries, heavy industries, residential, vehicular, and commercial. Thermoelectric power plants. Transport systems, pipelines and multimodal transport systems using vehicles. Pumping stations, compress the gas to transport it, and ports, receive and or ship liquefied natural gas, LNG. They are associated with liquefaction and or regasification plants and have gas storage capacity. Connectivity between the electricity and gas sectors occurs through the demand for natural gas for use in thermal plants, and the substitution of the demand that can occur between gas and electricity. Electricity system and wholesale market mathematical models. Traditionally, the optimization models in the electricity sector have been individual modeling with exogenous coordination between models, based on multi-stage stochastic programming, and using large-scale optimization methodologies. The differences provided by high power are integrated holistic modeling, scientific risk modeling, multidimensional uncertainty, parallel optimization, and autonomous real-time distributed optimization. The EED, electricity economic dispatch, model optimizes the dispatch of generation infrastructure, minimizing the cost of operating the electricity system, which simulates a perfect electricity market. EAT is the core model of high power, as its equations/constraints are used in multiple specific models that the agent requires to address decision support needs. From EDD, 3 models of complementary dispatch are built: economic perfect dispatch, economic regulated dispatch, Nash-Carnot equilibrium dispatch, and unit commitment. The first 3 models are oriented to planning and the fourth to real-time programming. All models that integrate high/power have been developed using the OPTEX GAMS interface. The integration of the models is carried out automatically by OPTEX, and the generated programs coordinate their communication through the database, using monolithic models, or in RAM memory using large-scale parallel optimization. All high/power models can run in deterministic, or stochastic, version with user-definable uncertainty dimensions. GAMS offers 4 group of tools for the GAMS users. GAMS Studio, Original IDE Interface, GAMS Miro, New User Interface, offered to the optimization market since 2019, GAMSP, tool oriented to Python modelers, and GAMS Engine. The screenshot corresponds to the traditional GAMS Studio IDE. The current OPTEX GAMS link is geared towards working with this interface. GAMS Miro is the deployment environment for the GAMS and GAMSP models. GAMS Miro desktop is installed locally on a computer, and it is an interactive interfaces for GAMS models and to deploy them locally or in the cloud. The GAMS Miro connector is the interface for communication between GAMS and Miro. This component takes over the data management on the GAMS side. GAMS Engine is a REST API designed to run in cloud environments. It is an enterprise-grade system that runs on a server and offers features such as high scalability, load balancing via a job queue, rolling updates and much more. GAMS Engine automatically schedules jobs and assigns them to an available GAMS worker to solve it. Also, it comes with a powerful user management system that allows you to restrict the activities of your users according to your organizational hierarchy. GAMS Engine can not only be controlled by a Miro application. Thanks to the use of OpenAPI, clients in various programming languages are available. GAMS Engine can not only be controlled by a Miro application. Thanks to the use of OpenAPI, clients in various programming languages are available. HI is working into interface OPTEX with the new GAM optimization technologies. Linking OPTEX to GAMS optimization technologies. The high-power database is part of a relational information system that integrates all high-power data. It is managed by OPTEX. It is called IDIS, Industrial Data Information System. In this regard, the following should be considered. The data model is defined in the OPTEX dictionaries, based on metadata from the fields in the tables. The basic structure of the data model can be generated by OPTEX. Alternatively, it can be built by the modeler, and OPTEX generates an access system, based on browsers, to manage the information system. This is part of artificial intelligence services that builds, online, as if it were a hologram, all the software to manage the information system. Initially, the OPTEX user interface was a data window to capture the contents of tables. The screenshot presents the master table of indexes, and all the tables with relationships with other entities, like variables, constraints, parameters, aliases, problems, data tables, and fields in the data tables. This vision implies thinking outside the box, since the relationships between mathematical elements are not investigated in the computer programs, but they are visualized in a holistic way through the exploration of a database. This input-output interface is generated online by OPTEX, which means that there is not a program associated with the windows, menu, shell and data, and their connectivity. OPTEX, as an artificial intelligence, interprets what is stored in databases, and generates a hologram adjusted to the application. As an output interface, it is still valid, due to the organization and ease of handling of any SQL database. Today the data is captured directly from MS Word, and soon it will be from ChatGPT. For more information on how to structure the formulation of a model in the OPTEX expert system, interested parties can watch the following videos. Making mathematical models using an optimization expert system. The models implemented in OPTEX can use multiple technologies, due to the clear division between mathematical model and optimization technology. Regardless of the programming languages, the models connect directly to the IDAS database by means of SQL statements. The screenshot shows SQL connectivity to the Industrial Information System in a GAMS program. Because the IDAS data model is open, the end user can connect it to any other application developed by a third party, this for any input-output data. The fundamental elements of the OPTEX architecture are a relational information system, which integrates two specialized information systems. Mathematical Modeling Information System, MMIS, stores the entire mathematical modeling environment, and Industrial Data Information System, IDIS, stores customer data. The next element is OPTEX, the generative artificial intelligence in charge of interpreting the existing information in the MES, and from there generating all the computer elements that are required for the user to interact with the DSS. Based on Open Database Connectivity, ODBC, OPTEX generates the following elements: visual interface for the user to access the IDAS to maintain and consult it. Interface for mathematical models to connect with the IDAS, generated following the syntax of each optimization technology. This interface is part of the computer programs of the algorithms. Below are several examples of this type of component, based on SQL statements. The image features standard OPTEX GAMS connectivity. OPTEX generates all GAMS programs in a multi-problem model, and the user selects the solver to be used. Program generation is done using OPTEX, which then generates all programs needed to run the model using GAMS, general algebraic modeling systems. OPTEX directly connects the advanced concepts of GAMS, so that the user can use them in the formulation of their model's advanced optimization methodologies, such as extended nonlinear programming, integrated complementary models, two-level programming, disjunctive programming, and others. This will not involve programming. The connection to the advanced GAMS concepts is carried out automatically by OPTEX. The data connection can be made through text files, .opt, which will be incorporated through the $include instruction, or reading directly from a SQL-like relational database. Electricity and natural gas dispatch. For example, to use disjunctive programming. The process is totally user-friendly. The steps to follow are: first, indicate in the master table of constraints the variable that will act as the logical variable of said constraint. It must be a binary variable, and second, indicate at the time of execution that disjunctive programming must be activated, for those constraints that have a logical variable assigned. The screenshot shows the code generated by OPTEX GAMS to perform the activation of disjunctive programming. Industrial Information System. If the modeler wishes, OPTEX automatically generates the Industrial Information System to store the input and output data to the mathematical models. OPTEX manages a metadata model that, automatically, generates a user interface that includes an Explorer menu to navigate the tables of the IDAS. That can be resident on various types of database servers. The screenshot presents the master table of reservoirs. The screenshot features a shell window that contains multiple data windows. In this case, the master table of reservoirs and its related tables. The screenshot presents the master table of hydropower plants. To handle multiple studies, the information system includes the concepts of scenario family, such as the 2014 studies for the expansion of the mod plan design, and the scenarios associated with each expansion plan studied. The OPTEX graphical user interface handles all the input and output data associated with each scenario. It is a similar concept to the GAMS Miro scenarios. These scenarios are considered as external to the model, and must be differentiated from the internal scenarios in a stochastic optimization model. The image presents the Results Table Explorer. These tables are incorporated directly by OPTEX into the information system. High Power Dispatch Model. GAMS programs. OPTEX manages 4 types of models, all of which are used in the high-power construction process. This is valid for any mathematical model made with OPTEX. Deterministic optimization model. This is the standard or core model, which considers a single internal scenario. Non-anticipative stochastic optimization model. Starting from the stochastic parallel model, a non-anticipatory response is required, that is, the decision depends on what is happening in the stochastic dynamic process. In these cases, each scenario has its probability, looking for a solution that optimizes a measure of system performance by integrating the scenarios, such as expected value or other statistics. The solution must be obtained by introducing a model coordinator aimed at ensuring the constraints of non-anticipation and the optimum of the objective function. Non-anticipative stochastic optimization model. Starting from the stochastic parallel model, a non-anticipatory response is required, that is, the decision depends on what is happening in the stochastic dynamic process. In these cases, each scenario has its probability, looking for a solution that optimizes a measure of system performance by integrating the scenarios, such as expected value or other statistics. The solution must be obtained by introducing a model coordinator aimed at ensuring the constraints of non-anticipation and the optimum of the objective function. Non-anticipative stochastic optimization model plus risk management. Finally, HI considers that stochastic optimization models, in their two versions, only make sense if risk management is included. For this reason, if the modeler requires it, OPTEX can automatically incorporate financial and/or operational risk management equations. This is the scope of the high-power models. High-power dispatch deterministic model. GAMS program generation. Deterministic models operate without cycles, solving a single monolithic problem, which has 3 steps. Pre-processing, reading the database and calculating everything that needs to be adjusted before performing optimization. Optimization, solving the math problem, and post-processing, calculation of result variables that are definitions that are not part of the model, and storage of this information in the database. This part of the program is presented below. The GAMS program is presented in parts, indicating in each case the content of the partial image. Model header and indexes declarations. Alias indexes declarations. Time standard parameters declarations and reading. Using an include file. Read sets declarations and reading. Read parameters. Transformation of read time series parameters. From the data read in the tables, OPTEX can calculate 3 types of dynamic parameters: impulse, polyline, and stare. Calculated parameters and calculated sets. OPTEX solves the correct order for declaring parameters, sets, variables, and constraints, considering the relationships between them. This is a common problem in other algebraic languages. Model variables declarations. Objective function variables. Model variables bounds. Constraints declarations. Initial stock restrictions declarations and objective function definition instructions. Constraints algebraic formulation. Conditions of existence constraints. Conditions of existence variables. Objective function equations. Creating CSV files. Model variables include. This code is included in the program using an include. High power dispatch, modplan model, transmission expansion planning. Peruvian transmission system. Project, electric and gas system and market dispatch for Peruvian transmission expansion plans. Challenge, to develop an integrated electricity and gas dispatch model to support the optimization of the national plan of transmission in Peru. Solution, design and implementation of a set of mathematical models that includes simulation of simultaneous optimum dispatch of electricity and natural gas systems, and the evaluation of multiple expansion uncertainty scenarios, to build Pareto curves that support the selection of a robust expansion plan. Result, ModPlan, a long-term stochastic parallel optimization model that includes simultaneous optimum dispatch of electricity and natural gas systems. The model was linked to the Excel environment used by the end user. Since 2014, ModPlan has been the official model, by law, used by ISO of Zine, to carry out transmission expansion plans. This project was executed by Decision Werelta, the parent company of HI. ModPlan is made up of three models. ModPlan Rates, version of the Perseo model, which a Synergman uses for the price analysis of the Peruvian interconnected system. ModPlan, the central model for the construction of transmission system expansion plans, and ModPlan Attributes, a post-processing model that produces indicators of the operation of the interconnected system, for the analysis of an external scenario of the expansion plan. The screenshots show the ModPlan control from an Excel sheet, which is used by the analysts who build the transmission expansion plan. The ModPlan model was developed using a high-power version mounted in OPTEX, as a starting point. COS-SYNEC, the ISO of the Peruvian electricity system, must build the expansion plan of the transmission system in accordance with the methodology specified by the Peruvian law. ModPlan considers two types of scenarios, internal and external. The internal ones are those considered by the stochastic optimization model. These are called by COS as futures, and are built based on multiple uncertainty dimensions. The model runs every certain number of years for an external scenario, which corresponds to a possible expansion plan. One of the external scenarios analyzed will be the solution suggested by COS for the expansion plan. The image presents two periods, 2020 and 2024, the first with 114 internal scenarios and the second with 216. Examples of dimensions of uncertainty: fuel prices, hydrology, demand, investment of generators, variation in the costs of works, and others. OPTEX does not impose limits in this regard, and the user can configure the number of uncertainty dimensions that are necessary. Multiple dimensions of uncertainty generate multiple loops in GAMS. OPTEX assemble the combinations to generate the different scenarios automatically. ModPlan can be solved without parallelism in a loop for all internal scenarios, occupying a single CPU thread. In the case of parallelism, it is necessary to modify the programming to handle the process. Multiple CPU threads are used, at least one thread must be free; if not, the computer will get stuck. No parallelism. ModPlan was deployed on a workstation with 12 cores using just one. This approach resulted in lower use of system resources and long solution time. Parallelly, 11 cores were allocated to ModPlan, increasing the system's resource usage and shortening the solution time. The speed of execution is a determinant of the number of expansion plans that can be studied, and of the internal scenarios that can be incorporated into ModPlan. The trend will be the growth of the scenarios in a similar way to how the power of computer technologies grows. ModPlan. Parallel and stochastic implementation using GAMS. In 2004, General Algebraic Modeling Systems Incorporated, GAMS, reported experiments in the speed gained using 200 CPUs in parallel was 60 to 1 times faster, with its corresponding benefit in accuracy, if parallel processing is used to increase the quality of the results. Stochastic parallel models involve the coordinated solution of multiple independent problems that can be solved sequentially or in parallel. The ModPlan model, developed for the ISO of Peru, works in parallel and was generated using OPTEX. This part of the program is presented below. The implementation of the parallel ModPlan was carried out by coordinating everything within a single GAMS program. The methodology consisted of programming, in the same program, a part of the problem startup using a traffic light system that informs the first core that is free. Another section of the program is aimed at results retrieving, asking the traffic light system to determine which cores have completed their task, to execute the recovery process. Using a single program, the two processes are performed sequentially, which can cause waits in the launch queue, or in the recovery queue. These timeouts can be eliminated, if OPTEX generates two programs, one aimed at launch and the other at recovery. High-power dispatch ModPlan parallel and stochastic GAMS program generation. The image presents the flow diagram of the two cycles controlled by the traffic lights. The OPTEX control window part. It is related to the activation of the parallel processing option, so that OPTEX generates the parallel code. This part of the program is presented below. As stated above, in the case of parallelism, it is necessary to modify the programming to handle the process. As you can see, the sequential and parallel solutions solve the same problem, but the data flow is different, since in the parallel case the processing is distributed in multiple core. The problems are deterministic, but they are indexed to the values of the uncertainty dimensions of the model, which vary with the outermost loop that must sweep the entire combinatorics of the values of the uncertainty dimensions. Then the strategy of parallelism will be to solve deterministic problems, as parameters of the uncertainty values. The screenshot shows the deterministic model variables declarations. The physical indexes are the same as those of the deterministic model. In addition, the indices of the uncertainty dimensions must be defined, which are 7, but 2 of them depend on other indices. Therefore, there are 5 effective indices of uncertainty. Since the deterministic problems do not contain the indices of the uncertainty dimensions, a RAM database must be created to store the results of each problem, containing the expanded indexes, physical entity indexes, in green, plus uncertainty dimension indexes, in blue. On the other hand, for each tuple of physical indices, at least the basic statistics should be stored. Value, average, maximum, minimum, standard deviation, in yellow. The screenshot presents declarations of statistical of the variables of stochastic optimization models. When solving a problem, it is necessary to store the results from the parallel solution. Creating CSV files deterministic model variables. At the beginning of the problem. At the end of the optimization process for all problems, statistics for deterministic model variables must be calculated. Deterministic model constraint declarations. Declarations of statistical of the constraints of stochastic optimization models. The control of sending problems to the core, and retrieving the results, is carried out using 2 loops, which work sequentially. Therefore, it is not possible to send and receive simultaneously. For this it would be necessary to generate other auxiliary programs. This possibility is faster. Before starting the loops, the modplan problem must be initialized, adapted to the parallel version. This involves defining aliases for indexes and sets that are required for parallel implementation. At the beginning of parallel optimization control, the first loop to be presented will be the recovery loop. Submitting process for parallel solution. The screen shows the opening of the loops of the dimensions of uncertainty, and recovery process for deterministic solution. Writing CSV files deterministic model variables. Storing general results for parallel solution. And closing loops. The second loop to be presented will be the launcher loop. Loops for generate the problem for each scenario. OPTEX automatically generates the pre- and the post-processing of the stochastic parameters and stochastic sets for each scenario. This involves solving the pre-processing of the mod plan. Next step is submitting process for parallel solution. Closing loops. The final part of the process has to do with performing the final calculations, closing files, and activating other processes. When finished the solution of all problems, it is necessary to execute the following process. Calculating statistics, closing files, and statistical files. The following screenshots show the code. Calculating statistics of the variables. Closing CSV files deterministic model variables. Creating, writing, closing CSV files with statistical variables. To end the process, it is possible to run a custom process, even by the user. High power dispatch model. Large scale optimization technologies. GAMS programs. Bender's partition theory. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. Given the complexity of the real world, which involves mathematical models of all types, linear, nonlinear, discrete, continuous, convex, non-convex, etc., it cannot be thought that with a single methodology, all the problems that make up an artificial brain can be solved. Therefore, it is required to have access to multiple large-scale optimization methodologies, which, using the principles of cross-decomposition, connect all mathematical problems, to perform autonomous distributed optimization in real time. With this approach, large-scale methodologies are incorporated into OPTEX, and through OPTEX, in GAMS. In the future, the real-life problem solution based on mathematical programming, applied to large physical and social structures/organizations, must be based on multi-level parallelism using the modern computational architectures. Then, large-scale optimization methodologies are the way to atomize an optimization mathematical problem in multiple types of subproblems that can be solved using the concepts of asynchronous parallel optimization and real-time distributed optimization. High power may use methodologies like Bender's theory, Lagrangian relaxation, Dantzig-Wolff decomposition, column generation, disjunctive programming and its variations. These methodologies may be combined using cross-decomposition concepts to implement parallel and/or distributed optimization. In Bender's decomposition theory can be considered three types of cuts. SBC, standard Bender's cut, corresponds to the methodology proposed by J.F. Benders. DBC, decoupled Bender's cut, corresponds to a variation of BT that solves in each iteration a small subproblem for each decomposition dimension. This is the cut that must always be applied, replacing the SBC, and UBC, unified Bender's cut, when the mathematical conditions are met, it corresponds to a variation of BT that solves in each iteration only one problem, or a subset of subproblems, and generates cuts in the coordinator for all problems. It applies to subproblems associated with periods, and/or random scenarios. Since 1980, Jesus Velázquez Bermúdez incorporated unified cuts into Bender's theory, which implies that by solving a single subproblem at the level of decomposition, if certain mathematical characteristics are met, it is possible to insert cuts in all subproblems. Next, the implementation in OPTEX of the hydroelectric model using the standard Bender's decomposition is presented. The model is called ModBenU and is conceived based on two problems. ModBenCo, which will be the coordinating problem and is related to the water system, and ModBenU, which will be the subproblem and is related to the electricity system. The screen shows the definition of the two problems, specifically ModBenCo. The constraints of each problem must be defined. Following the partitioning logic, OPTEX can define the decision variables in each problem, and the interconnection variables between problems. The second step is to define the problems that make up the model. That's all. The display corresponds to the header of an OPTEX GAMS using standard BT. Stochastic programming. In the field of mathematical optimization, stochastic programming, SP, is a framework for modeling optimization problems that involve uncertainty. The most used method is scenario-based SP, also known as non-anticipative stochastic programming. In this case, SP considers multiple scenarios, associating each of them with a probability of occurrence, and the model determines the best decision before the occurrence of the scenario, non-anticipative decisions. In OPTEX, the first step in implementing stochastic programming is to select the deterministic model that you want to convert to stochastic. The second step is to parameterize the uncertainty environment that converts the deterministic model into a stochastic one. Main aspect are: decision tree indicates how the model makes decisions. Stochastic process, the uncertainty dimensions must be defined by the users, considering which is the more real stochastic process. Risk management, the biggest advantage of stochastic models is the inclusion of risk measures in the stochastic model. Nowadays, the risk measure most used is the conditional value at risk, CVAR. Solution process, the solution approach of the model is an important point to consider. There are multiple alternatives, the selection is typical of experts in highly complex mathematical modeling. Below is the definition of a stochastic optimization model in OPTEX. The first step in formulating a stochastic optimization model is to define the uncertainty dimensions and the index with which they will be handled. The screenshot presents the definition of a multi-stage decision tree. It is defined. The decision tree code and its description, non-anticipative variables, and the stochastic parameters, together with the indices of the uncertainty dimension to which they belong. The next step is to define the connectivity of the nodes and branches of the decision tree, including the probability of each node. The fields associated with the uncertainty dimensions must be included and filled in the tables of the industrial database. The last two steps are: link the model to the decision tree, and define the C-var risk constraint. That's all. Non-anticipative constraints formulation. This constraint guarantees that the values of the non-anticipative variables are the same for all internal scenarios belonging to a given set. Those interested in learning more about the implementation of stochastic optimization models in OPTEX may consult OPTEX Mathematical Modeler's Manual. Making Stochastic Programming Models Filling the Blanks. GSDDP. Generalized Stochastic Dual Dynamic Programming. GDDP. Generalized Dual Dynamic Programming. And, in 1991, Jesus Velasquez Bermudez, founder and chief scientific officer of HI, developed the first version of what would end up being called GSDDP, Generalized Stochastic Dual Dynamic Programming. They are variations of Bender's partition theory, which were formally published in 2002. GSDDP includes risk management, from a scientific approach, using the conditional value at risk. The following table and image resume the study of behavior of GSDDP for a stochastic mixed linear economic electricity dispatch. The decrease in the solution time per scenario, when increase the number of scenarios, is a measure of the learning capacity of the GSDDP. Multi-level Bender's decomposition theory. Since the programming of the first version of OPTEX, the so-called multi-level Bender's decomposition theory was implemented, which generalizes the Bender's theory to multiple levels of partitioning and decomposition. Multi-level theory is based on the application of standard Bender's theory, in which the problem is divided into two. Bender's theory is applied again to the subproblem, and so on until it reaches the lower level of the system, that is, the atom of the system. If the partition dimension is time, the multi-level approach is similar to stochastic, dual dynamic programming, SDDP, a methodology widely used in the electricity sector. However, the multi-level scheme is more powerful than the SDDP, nested Benders, which only accepts diagonal arrays with lag of one period. Multi-level theory accepts triangular matrices with any number of lags. Joining the decomposition and the partition theories can be structured complex multi-level models. The case of a system expansion problem is analyzed. It can be an electricity and gas system. The first partition that can be made is according to the type of problem. Investments and operations. The next partition would be based on the sectors, which facilitates the decomposition into as many subproblems as sectors. There could be another level of partitioning depending on the zones in each sector. Finally, the problem can be broken down from the planning horizon periods. If the model is stochastic optimization, by scenarios, there are multiple built-in problems for different random conditions. The model can be broken down into as many problems as random conditions. Each problem will be the same as the original deterministic problem and can be solved using the same approach. These systems are characterized by the set of problem families that they include. Each color represents a type of optimization problem, related with a physical entity, or a decision level. Speed up ModPlan through ModPlan GSDDP. The standard parallel version of ModPlan can be accelerated to further reduce the execution time. To do this, GSSDP technology, developed by HI, may be incorporated. The idea is to include an artificial hypothalamus that accumulates information from all the problems executed, to speed up the solution of the remaining problems. This RAM database would store the dual and primal variables to incorporate cutting planes as new problems arise. The grouping of problems into families that meet specific math characteristics allows the use of GSDDP with unified Bender's cuts. A possible multi-level partition of the electricity dispatch problem would be general coordinator, generation system, and transmission system. In this case, the decomposition level of the generation can be solved using decoupled Bender's cut. For the transmission level, we can think of unified Bender's cuts, since, normally, the physical transmission system remains constant throughout the planning horizon. All these processes will significantly increase the speed of problem solution. As in the current version, OPTEX would generate all the mod plan code, including large-scale algorithm improvements. The power of enterprise artificial brains. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. This allows us to talk about autonomous real-time distributed optimization. Algorithms swarm, the actual state of artificial intelligence using artificial brains. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.